We'll be looking at the June 2019 multiple choice questions. Question 1. In the diagrams below, each box represents an orbital, and each electron is shown as an arrow. Which diagrams show the correct arrangements of electrons in an atom of carbon? You see, carbon has 6 electrons. That's the atomic number of 6. It can't be the first one because the orbitals are filled in increasing order of increasing energy. 2s has to be completely filled before it can move on to the next one. So it's not A. Again, the 2s subshell is not filled before it moves on to the 2p. So this, not this one as well. Now, you see with why it can't be C is because when you have more than one orbital at the same energy level, in this case 2p, all the orbitals are occupied in a single manner first. Like passengers on the bus, they don't know each other, they don't want to sit next to each other. They will only double up when they have to. And so it's going to be D. Moving on. Which statement about the reactions of halogens with halides is correct? You see, the wording of this can be a little bit tricky, so let's try to break this down. First of all, iodine cannot react with bromide because it is less reactive, so it just wouldn't react. Chlorine can reduce Br minus. Let's see what that means. Chlorine can react with Br minus, but it doesn't oxidize Br minus. It doesn't, reduce Br minus. What does reduce mean? Reduce is rig. Reduction is gain. Can reduce, it's saying that it's implying Br minus is going to gain another electron. No, it's not. Why can't it be the last one? Because chloride ion, iodine is less reactive than chlorine, so it cannot react with a chloride ion. Why is it C? Is because the bromide ion can reduce a chloride ion, meaning the chlorine. It can reduce the chlorine because chlorine will gain an electron. Again, rig. And because chlorine is more reactive than bromine. Answer is C. That's question 2, and that's correct. Next question. One molecule of a gas has a mass of 2.658 times 10 to the minus 3. What is the possible formula of the gas? What we're going to do here, this is the mass of one molecule. That's for one molecule. Let's see what the mass would be for 1 mole. So we multiply it by Avogadro's number. That gives you 16.00116. If you look at the molar masses, that's 32 plus 48, which is about 60. 32 plus 48, that's about 80. That's about 64. This is 32. This is 16. Answer will be A. Yep, and the mark scheme supports that. Now, in this question, in a lab, acid spills can be cleaned up and made safe by spreading anhydrous sodium carbonate. Anhydrous sodium carbonate is this formula. A student accidentally spills hydrochloric acid. You see hydrochloric acid reacts with sodium carbonate in a 2-to-1 ratio. Is that balanced? I believe it is now. So, what is the minimum mass of anhydrous sodium carbonate required to neutralize the acid? You see, from the acid, let's work out how many moles this is. Volume times concentration. That gives you the moles HCl. You see HCl reacts in a 2-to-1 ratio. And so, if we divide that by 2, that's the number of moles of sodium carbonate that will be needed, moles. But we want the mass. So let's then multiply it by the MR of sodium carbonate. 23 plus 23 plus 3 oxygens. No, a carbon and 3 oxygens. Let's see what that gives us. Of 5.3. That answer will be B. 4B, and that's correct. What is the oxidation number of N nitrogen in an hydrated magnesium nitrite or nitrate? I was about to reveal the name, but let's work this out. You see magnesium, we can disregard the water. Magnesium is a 2+ ion, and these special nitrate ions have a -1 charge each. And if you break it down, each oxygen is -2, -2. That means nitrogen must be +3 for the overall charge to be -1. So it will be +3, 5B, and that's correct. Moving on. The first reaction is a precipitation reaction. No change in oxidation numbers happening, testing for a halide. The second one, if you see, only the H+ and the Na is swapping around. So you could even say like almost like a acid-base reaction. C, let's look at C. The sulfur has an oxidation number of, well, that's -2, -2, -2. That's +2. So sulfur must be +4. If sulfur is +4 there, hydrogen doesn't change, chlorine doesn't change. Here, sulfur is -2. Sorry, oxygen is -2 each, and sulfur must be +4. Yep, no change. So it's not the first 3. The last one, copper is +2 here because oxygen is -2. It's 0 here, and nitrogen is 0 here because it's in its standard state, and it's -3 here because each hydrogen is +1. So the last reaction is a redox reaction. 6D. Yep, and that is correct. Which set of elements in the solid state contain a simple molecular lattice, then a giant covalent lattice, and then a giant metallic lattice? So a simple molecular lattice can be sulfur in the form of S8 molecules, P4 molecules, S8. Can't be the last one because that's a metal, magnesium. Let's look at the next one. The next one needs to be giant covalent. Yes, it is. Yes, it is. Phosphorus is not a giant covalent. And the last one, so it's out of A and B. The last one is supposed to be a metallic structure. Carbon is not a metal, whereas aluminium is. 7A. Yep, and the mark scheme supports that. Uh-oh. You've got a group 2 metal that is reacted with an excess of chlorine. The reaction forms this much of the chloride. What is the metal M? You see what we do here? Let's work out the mass of chlorine that's added on. So you've got chlorine, or the chlorides. Let's divide that by 35.5. And it's a group 2 metal. That means metal M is a 2+ charge. And the chloride ions, there will be 2 of them. So oops, I missed something out here. So it'll be 9.775 minus 3.528. That will give you the mass of the chlorine that's been added. Let's divide that by 35.5. You see, this gives you the moles of chlorine that's been added. The moles of chlorine is in a 2-to-1 ratio. 2-to-1 ratio. And so we divide that by 2. That will give you the moles. And what we do, again, mass over number of moles gives you the MR. The mass is, so let's do this, 9.755775 minus 3.528. Let's divide that by 35.5. Let's divide that by 2. That gives you the moles of the metal M. And then we do 3.58528 divided by that mole answer. That gives us 40.0973. So the nearest one is 40.1, which is calcium. The answer is B. Okay, B. And the mark scheme supports that. Moving on. Which statement is not correct for group 2 hydroxides? Magnesium hydroxide can be used to treat indigestion. Yes, it can. This is correct. Calcium hydroxide is used in agriculture to neutralize alkaline soil. No, it doesn't. Because calcium hydroxide is an alkaline itself, and adding it to alkaline soil would make it even more alkaline. So this is not true. The anion in strontium hydroxide contains 10 electrons. You see the oxygen has 8 electrons here. It gains 1 electron from hydrogen and 1 electron from outside. Let's put the hydrogen here. And then you've got a -1 ion there. And if you count the electrons, that adds up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, my phone is buzzing. Let me turn it on silent. And the last one, barium hydroxide is a product from barium and water. Yes, it is, because barium, when it reacts with the water, it gives you hydrogen gas, and it gives you the hydroxide. And to balance, we can put a big 2 there. So the answer is B, which is not correct. Yep, mark scheme supports that. Next question. Right, even this is a 1 marker. In the exam, you would have probably about just really a minute to answer this. Less than a minute, sorry. Less than a minute. Let's say a minute to answer this. There's quite a bit going on here. It's asking, what is the energy released in kilojoules during the breakdown of this much ozone? You've got a molar gas volume in the ozone layer is approximately 2.5 meters cubed is 1 mole of gas. It's in a 2:3 ratio here, and this is how much energy is released. How do we do this calculation? 1.0 meters cubed divided by 2.5. You see, if you look at the units, that cancels out with that. And because you're dividing it by a mole to the -1, that gets flipped to the top as mole. So this answer gives you the moles. Now, this is, you see this over here, this is per 2 moles of ozone. So if we divide the answer by 2, and then multiply it by -284, that will tell you how much energy is released. My answer is -56.8. That means energy given out. The minus. And the nearest answer we have here is A. Yep, the mark scheme supports that. Just a reminder that why do we divide by 2? Because of this 2 over here. This equation is for 2 moles of ozone breaking down, not 1 mole. Moving on. We're using the Arrhenius equation here. Arrhenius equation in the form of y is equal to m times x times plus c. Bit of GCSE maths here. And what is y is ln k, or natural log k. M is the gradient, which is minus, and then you multiply by x, which is 1 over t, and then you've got your y-intercept, which is natural log of a. So if the gradient is given as -4420, and they want it in kilojoules per mole, what you do is -4420. Let's multiply this by minus R, which is 8.314. That gets rid of the R and gets rid of the minus sign and gives your activation energy in joules per mole. -4420 8.314. Yep, and divide that by 1,000. This is 3674. 8 divided by 1,000. 7, which we got here as here. If we put the R in, that'd be the wrong answer. If we forget to put the minus in front of the R to get rid of the minus, get rid of this minus.